Good day. Today we'll discuss sample size calculation. And let me share my screen. Okay. So just to acknowledge my friend from St. Luke's, the first 3 slides came from her, were taken from her. Now, when should sample size calculation be provided? Sample size calculation is provided for or required for quantitative studies like cross-sectional studies, case control studies, cohort studies, or clinical trials. It may not be required for qualitative research with formal qualitative methods such as content analysis and ethnography. You see, the reason why we calculate for the sample size is that we want to generalize results from samples to population. And in quantitative studies, we can generalize results from samples to population. But in qualitative researches, we don't intend to generalize our results because it is just a qualitative research. Well, it's a qualitative research, put it that way. And so we don't need to generalize results from samples to population, and sample size calculation may not be required. It may not also be required for certain preliminary pilot studies because it is only a pilot study. Now, but we can, for those, if you want to calculate for the sample size for quantitative research, it may still be calculated, and the following must be specified in the sample size calculation section in the proposal: that the sampling strategy and the sample size are based on similar published literature and very much the same as in quantitative research. And the sample size is tentative and likely to change through the process of research. Now, for feasibilities and pilot studies, again, sample size calculation may not be appropriate, but we can have a median sample size for pilot study for 2-arm trials. If the outcome is dichotomous, presence, absence, we can have 36 per arm or 30 per arm for quantitative outcomes, for if the outcome is continuous. Now, in the sample size calculation, and we are now talking of quantitative research, the formula for the sample size depends on the following: the parameter that you want to estimate, and the parameter is based on can be seen from the objective of the study, because we will calculate for our sample size based on the objective of the study. So what is the parameter that you want to estimate in that objective? And the formula depends precisely on that parameter. And then the type of the research design that you use, because if a research design will make you collect data prospectively, will allow you to collect data prospectively, we need a much larger sample size. And then, of course, the sampling methodology. And in the sample size calculation, I just would want to emphasize to you that the population size is not considered in the formula. You don't consider the population size in the formula. Now, some generalities in the sample size calculation: the rarer the condition, the larger the sample size. The more complex data analysis require larger sample size than simple analysis. So if the analysis requires multivariate analysis, and then the sample size will be much larger. The more heterogeneous the values of the parameters are, So for example, we are talking of a high standard deviation. Standard deviation is a measure of heterogeneity, and then the larger the sample size. In general, longitudinal studies require a larger sample size than case control and cross-sectional study. Longitudinal studies where we collect data prospectively, and because there can be losses to follow up, so we require larger sample size. And so it's a good practice to provide a correction factor for non-response or refusal rate in the estimation of the sample size. So we need to give a correction factor. And normally, what I use is to add 25% for defaulters, for losses to follow up. I add 25% in the sample size that I calculate. The higher the level of accuracy and precision that the investigator desires, for the resulting estimate, the larger the sample size. And later on, we'll show to you that if we increase the level of precision or the level of accuracy, the sample size, the larger will the sample size be. And sample size will be a compromise between the different ends, the different computed sample sizes, and available resources, meaning that the final sample size will ultimately depend on the available budget and other resources that will effectively implement the study. And I will show to you how we can change the different computed sample size that will really depend on the availability of budget. Now, we now talk of the sample size estimation. And basically, we have two types of sample size estimation: the estimation problem and hypothesis testing problem. For estimation problem, we have two. If we are estimating for the population mean, we have quantitative data. Or if we are estimating for the population proportion for qualitative data. And we can also have, when we have problems of hypothesis testing, we test hypothesis for the difference between two means, again, quantitative data, and we test for hypothesis for the difference between two proportions, we test qualitative data. For both sample size calculation, test of hypothesis for the difference between two means, and test of hypothesis for the difference between two proportions, the number is multiplied, the sample size that we calculate is multiplied by the number of groups. So if we have two groups, we normally multiply the resulting sample size, the resulting n, by the number of groups. Now, let's go to the first to estimation problem. We estimate the population mean. And this is the formula, but I won't bother you with this formula. You don't have to memorize this formula because I have automated the formula, which I will show to you in class. But just to explain to you the formula, the n is the sample size, the z is the reliability estimates. Later on, we'll show to you the different values of the reliability estimates z. And then the S, the S is actually the standard deviation. When you square the standard deviation, you have the variance. And then the D will be the maximum allowable error. Now, these are the different Z values for the different reliability. So for 80% reliability, the Z value is 1.29. For 90%, 1.64, and so on and so forth down the line. Now, let's give an example. Suppose the objective of the study is to determine the mean baseline central retinal thickness among patients given Avastin. Avastin is a chemotherapeutic drug that is normally given for colon cancer. But ophthalmologists use Avastin to treat, as an off-label drug, to treat macular degeneration. So this ophthalmologist wants to determine the mean baseline central retinal thickness among patients given Avastin. So that is the objective of the study. And to calculate for the sample size, he needs to make an estimate, well, of the maximum allowable error of the mean baseline central retinal thickness. That is a plus or minus value of the mean estimate. And that is decided upon by the researcher. So that's an arbitrary value decided upon by the researcher. And he also needs the standard deviation taken from previous studies, standard deviation of the central retinal thickness taken from previous studies. And so if he likes his estimate to be plus or minus 30 units of the true value, this is the maximum allowable error. And with a reliability of 95% and a standard deviation of 176 taken from previous studies, he can calculate how many patients will be needed in the study. And so using now the formula, he will need 133 patients. Now, as I said, I have automated the formula. I made a sample size calculator in Excel, and I will show that to you in class. Let's go to the next estimation problem, estimating the population proportion. And the outcome of interest here, as I said, is a qualitative variable in dichotomous presence or absence of something. And this is the formula. Again, I don't want to bother you with the formula. I want to ask you to memorize the formula because I have automated the calculation. But just to explain to you what the formula means, the P is the population estimate of the true proportion. So that's the estimate of the true proportion, population proportion. And then the Q is just 1 minus P. So that if the proportion is, say, for example, 70%, normally we report it in decimals of 0.7, Q will just be 1 minus 0.7 or 0.3. So Q is equal to 0.3, such that if you add Q plus P plus Q, that should equal to 1. And so let's give an example. A biochemist wishes to estimate the prevalence of zinc deficiency among diabetic patients. Okay, so this is the objective of the study. And so he needs to get the prevalence of zinc deficiency among diabetic patients from previous studies. Suppose the prevalence in a related study of zinc deficiency is 10%, and the desired precision or the maximum allowable error is plus or minus 3%, and a reliability of 95%, he can calculate how many participants should be included in her study. And so, using now the formula, the sample size calculated. This is the P, this is the 10% prevalence, 10% or 0.1, and then this is the Q, 1 minus P is 0.9, and then this is the maximum allowable error, 3%, and then the sample size is 385. As I said, I have automated that. We'll show to you the calculator later on in class. Now, let's go to the problem of hypothesis testing. So we test hypotheses. And these are the factors that we need to consider in the computation of the sample size for hypothesis testing. The alpha error, that's denoted by Z sub 1 minus alpha. The beta error, that's denoted by Z sub 1 minus beta. And the beta error is also called the power of the test. And then the effect size will just be the difference, if we are talking of quantitative data, just the difference between the two means, the mean for the first group and second mean for the second group. The effect size will just be the difference between the two, mean difference. And then the type of alternative hypothesis, whether it's one-tailed or a two-tailed alternative hypothesis, and then the variability as measured by the standard deviation. So this is the formula for the test of hypothesis for the difference between two proportions. And again, this one is the alpha error, the beta error of the power of the test. This is your standard deviation. When you square the standard deviation, that should be the variance for the first group, and then the variance for the second group, and then the mean difference, and then the difference should be, the difference between the two means should have clinical significance. So we need to have a difference that has clinical significance, because if the difference is just too small, the sample size will be very, very high. And if for example, we're able to attain the calculated sample size that is very high, and then we might get a statistically significant difference, but it may not be clinically, the difference may not be clinically significant. That is why the difference that you need to put here will have a clinically significant difference. That's your effect size. Let's give an example for the test of hypothesis for the difference between two means. An ophthalmologist wants to determine if there is a difference in the percent reduction of central retinal thickness among patients given less than 4 injections of Avastin after 1 month of treatment versus those given 4 or more injections. As we said a while ago, Avastin is an off-label drug that ophthalmologists use for macular degeneration, except that that drug will result to thinning of the retina, of the central retina. So there will be a reduction in the thickness. So that is one of the side effects of this Avastin, that they normally inject intravitreally. They inject intravitreally. And so this ophthalmologist wants to compare the difference in the percent reduction of the central retinal thickness among patients given less than 4 injections versus those given 4 or more injections after 1 month of treatment. And so these are the things that he needs. Okay, the power, the alpha error. Normally, the alpha error is taken from previous study. The alpha error is normally decided upon by the researcher. So with a very small alpha error, 1%, the larger the sample size. Then the power of the test, again, decided upon by the researcher. If the power of the test is high, 95%, for example, the sample size will be high. And then the effect size, which is 10%, this is the effect size that the researcher thinks that has clinically significant difference. And then the alternative hypothesis, two-tailed, and the standard deviation 10 taken from previous studies. Okay, using now the formula, the sample size is 31 patients per group. And we said because there are two groups, those given Avastin for less than 4 injections, and those given Avastin for 4 or more injections after 1 month of treatment. So we multiply 31 by 2, and so we have 62 for 2 groups. And again, we'll show to you the sample size calculator in class. And lastly, this is the test of hypothesis for the difference between two proportions. These are qualitative data, and I don't want you to memorize again the formula. Just to explain to you what the formula means. Okay, the P, as we said, is the population proportion of the first group. The Q, this should be Q sub 1. The Q sub 1 is just 1 minus P sub 1. And then the P sub 2 will be the proportion for the second group. And then the Q sub 2 will be just 1 minus P sub 2. Now we have here the Q bar, the P bar, and the Q bar. The P bar is actually the average of P sub 1 and P sub 2, the average of P sub 1 and P sub 2. So that's the P bar. And then the Q bar will just be 1 minus the P bar. Okay, and then again, this is the difference in the proportion. This is your effect size. And again, the difference in the proportion should be clinically significant. So we'll give an example. A hospital administrator wants to compare the incidence of neonatal infections among premature babies with one group of babies breastfed fully and the other group bottle fed. So two groups of babies, of premature babies, two groups bottle fed, one group breastfed, another group, and we want to compare the incidence of neonatal infection. Okay, now these are the things that he needs. The alpha error, again, dictated upon by the researcher, that's 5%. Power of the test is 90%. And the incidence of neonatal infections among premature babies is 25%. This is taken from previous studies. And then breastfeeding is hypothesized. This assumption will be decided upon or can be decided upon by the researcher. And breastfeeding is hypothesized to reduce the incidence to 15%. So from 25% incidence to 15%, or an effect size of 10%. 25 minus 15 is 10%. And the type of alternative hypothesis is one-tailed, and then the sample size calculated is 271 per group. But because we have two groups, we normally multiply this by 2, and so we have 542 for two groups. And so this is the using the data, we have this, and then we have 271 patients per group. We multiply this for two groups, so 542 for two groups. Okay, and we'll show to you the calculator in class. And then how do we now write the sample size calculation? And we'll just show to you the write-up of the sample size calculation for this objective. The objective of the study is to compare the incidence of neonatal infections among premature babies with one group of babies breastfed fully and the other group bottle-fed. So this is how you do the write-up. Sample size was calculated based on the comparison of the incidence of neonatal infections among breastfed premature babies versus bottle-fed babies. Suppose neonatal infections in bottle-fed babies is 25%, and you normally cite the source, so the author and the year when it was published. And among breastfed babies, we hypothesize that incidence be reduced to 15%, so an effect size of 10%, with an alpha error of 5%, power of 90%, and a one-tailed alternative hypothesis. The sample size required is 271 per group, or 542 for two groups. Now, just a note, if we do a multivariate analysis, we need to add 20 to 25% per variable that you control. And that is the reason why I told you that those that require complex data analysis will need larger sample size, because when we do multivariate analysis, we normally add 20 to 25% per variable that you control. So that if the sample size calculated is 542, and we want to control for 4 more variables in the analysis, we add 25% for each control variable times 4. We have 4 variables to be controlled, so that is 100%. And so the sample size, the final sample size required will be, we add 100% or times 2 of the 542, and so the final sample size becomes 1084. And this is how we write it, controlling for 4 more variables in the analysis and adding 25% for each variable that you control. Final sample size is 184. That's actually the last slide, and I will end here and we'll show to you the sample size calculation in class, and then we'll show you more examples for you to be able to understand sample size calculation. I hope that this lecture will help you calculate the sample size yourselves. Thank you.